Picture a medium-sized tech company. They have a PostgreSQL database for their primary records, an Elasticsearch cluster for full-text search, a Redis cache for fast lookups, a data warehouse in Snowflake for analytics, maybe a Neo4j graph database for recommendation logic, and a Kafka stream for real-time event processing. That's 6 systems. Every one of them holds a version of the same customer data. When a customer updates their email address, which system is the source of truth? How do you make sure all 6 reflect the change? What happens if the cache update succeeds but the search index update fails? This is the central problem of Chapter 12. No single tool satisfies all data storage and processing needs. Kleppmann opens the final chapter with a blunt observation. A recurring theme across the entire book is that for any given problem, there are several solutions, all of which have different pros, cons, and trade-offs. Even a so-called general-purpose database is designed for a particular usage pattern. The solution the book proposes is not to find one database that does everything. That path, Kleppmann argues, almost guarantees a poor implementation. Instead, use the right tool for each job, and keep data in sync by deriving it. The OLTP database is the system of record, the authoritative source. Everything else is a derived dataset. Here's the key insight: if you can funnel all user input through a single system that decides on an ordering for all writes, it becomes much easier to derive other representations of the data by processing those writes in the same order. This is the state machine replication approach. Change data capture (CDC) from the primary database to all derived systems gives you exactly that, a single ordered log of changes flowing outward. The challenge of keeping multiple specialized systems in sync is fundamentally a data integration challenge. And the answer is data flow. Data flows from the source of record outward to derived datasets through deterministic, replayable pipelines. That's the architecture we'll explore in this section. In 2011, Nathan Mars proposed an elegant answer to a hard question: how do you get both accuracy and low latency when processing large streams of data? His answer was the Lambda architecture. Run 2 processing systems in parallel. A batch layer using Hadoop MapReduce reprocesses the full historical dataset periodically, producing a correct, complete view. A speed layer using Storm processes events as they arrive, producing an approximate but fast view. At query time, you merge the results from both layers. The reasoning was sound. Batch processing is simpler and thus less prone to bugs. Stream processors at the time were thought to be less reliable and harder to make fault tolerant. Let the batch layer handle correctness, let the speed layer handle freshness, and merge them together. The Lambda architecture was genuinely influential. It popularized the principle of deriving views onto streams of immutable events, a principle this entire chapter is built on. But Kleppmann argues it has serious practical problems. Here's the most damaging one: you must maintain the same logic in 2 completely different systems, a batch framework and a stream framework. They use different APIs, different abstractions, different failure modes. Debugging requires understanding both. Tuning requires understanding both. And here's the subtle trap: the 2 systems often produce slightly different results, because the exact semantics of joins, aggregations, and windowing differ between batch and stream implementations. So the merge step is comparing 2 slightly wrong answers instead of one right one. J. Krebs identified a better path. His insight: if you use a log-based system like Kafka, you can retain the full history of events. Replaying history through a stream processor is the same operation as processing new events. The log is the batch. You do not need 2 separate systems. This observation led directly to unified processing frameworks like Apache Flink, which runs the same code on both historical and live data: one codebase, one mental model, one set of semantics. The Lambda architecture solved a real problem. Flink dissolves it. Apache Spark performs stream processing on top of a batch engine by breaking the incoming stream into microbatches. Apache Flink takes the opposite approach: it performs batch processing on top of a stream engine, treating a bounded historical dataset as a special case of an unbounded stream. In principle, as Kleppmann notes, one type of processing can be emulated on top of the other. This convergence matters because it dissolves the Lambda architecture's core problem. The goal of data integration is to make sure that data ends up in the right form in all the right places. Batch and stream processors are the tools for achieving this goal. Their outputs are derived datasets, search indexes, materialized views, recommendations, aggregate metrics, machine learning models. Think about what reprocessing enables. Without the ability to reprocess historical data, schema evolution is limited to simple changes: adding an optional field, adding a new record type. With reprocessing, you can restructure a dataset into a completely different model to better serve new requirements. Derived views allow gradual evolution. You can maintain the old schema and the new schema side by side as two independently derived views onto the same underlying data. Shift a small number of users to the new view, test it, then gradually increase the proportion until you can drop the old view. Every stage is reversible. Klutman uses a vivid historical analogy, the Great British Railway gauge conversion of 1846. Different railway companies had built tracks with different gauges, the distance between the two rails. Trains built for one gauge couldn't run on another. After a single standard gauge was finally decided on, the solution was to convert tracks to dual gauge by adding a third rail, allowing trains of both gauges to run simultaneously. Gradually, all tracks were converted, and the non-standard rail was removed. The BART system in the San Francisco Bay Area still uses a different gauge from most of the US because migration is expensive. Data systems face the same challenge. The answer is the same: gradual, reversible migration via derived views maintained side by side. That's the power unified batch and stream processing unlocks.